Okay, after that side excursion into the sun itself, we'll return to the one problem and the one part of the sun, which is the core and what really makes it happen, that affects what we're talking about now, and that's neutrinos and neutrino physics. So in the core of the sun, you remember that was just in the very, very middle of the sun. It's very massive, and it's a place where then we can have reactions, nuclear reactions happen, and in fact, it's dense enough to basically have something that's very hard to reproduce on Earth, but we've done it, which is to have the fusion reaction happen naturally. And so the main reaction, nuclear reaction that happens, that basically is responsible for the engine that makes the sun make the heat and energy, is the fusion reaction. I've drawn it here. It's 4 protons coming together and fusing into helium-4. So we make helium-4, which is very dominant and ends up coming out as the gas of the sun. As a fusion process of it, it releases 27 MeV in energy. That's the extra energy that comes out then, that produces the heat and light, and produces some secondary particles, positrons and neutrinos. And since it produces positrons, the neutrinos will be solely and only electron neutrinos. Remember that I keep showing that when we make electron neutrinos, they always are associated with electrons. So we make muon neutrinos, they're associated with muons. At birth, and we saw that in the muon neutrino one, where I showed you that if you make a beam of particles on an accelerator and they have muons made with them, because the muons come from the decay of pi mesons, they don't decay and make electrons, they make muons, then those neutrinos, when they interact, always make muons. They're associated with that solely. So the electron neutrino is the one in this case that's made. So the solar neutrinos are produced in this electron process. The neutrinos themselves are responsible for 98% of the energy that's produced in the sun. So that's a kind of sobering fact, since we find them so hard to detect and so forth. But as I say, most of the energy in the sun goes out in form of neutrinos. The sun emits light, which is what we use all the time, because the nuclear fusion process produces a lot of energy, and that energy produces light. So this is, again, writing it more in formula. We start with 4 protons. They fuse together in the density that's in the core. They make 2 positrons, and 2 neutrinos in addition to the helium-4 itself, and release 25 MeV of energy. And these are the electron neutrinos. Now, coming to what we're doing, which is not studying the sun, but using the neutrinos that come from the sun, then in looking in all the ways that I showed you at the sun, if we really want to understand how the sun works, we should see the electron neutrinos that come out. So this was the motivation for some very ambitious experiments once people had discovered the neutrinos, which is that to understand whether we really understood how the sun burns once we had detected neutrinos, to try to detect the neutrinos that come from the sun. And those neutrinos should be electron neutrinos. So we make a detector that can detect electron neutrinos, and that's what was done, and I'll show you that. The flux of it can be calculated by the energy of the sun and so forth. So we know how to calculate from the temperature of the sun, the size of the sun, amount of material in the sun. We know how to calculate how much energy is going to be released, and that's all done through the fusion reaction, and this is just the numbers. The mass loss is converted to energy, and we know how much energy comes out of the sun. So the sun has enough mass to go for another 5 billion years, so it will eventually burn itself out. Whether we'll last 5 billion years to go with it is another serious question. But the sun isn't imminently going to fail. So when you have this reaction then in the center of the sun, the one that I showed you is called the PP reaction. Notice on the left here, this is a logarithmic plot. So the scale on the left is logarithmic. And what's shown here is the typical energy is in the MeVs. Something like between a fraction of an MeV out to somewhere like 10 or 15 MeV. And the main reaction, this is many decades in logarithms, is this one here. And that's the one that I showed, the proton-proton reaction. And it's the dominant thing that happens in the sun. But then as things propagate, there are other reactions, and those are shown here. There's one that makes boron 8, one that makes the highest energy neutrinos, one that's beryllium 7, and so forth and so on. So if you study all the nuclear physics that happens in the sun itself, there's a whole spectrum of neutrinos that come out. They'll look like this. It's dominated by the one here, which is the most by orders of magnitude, but it's very, very low in energy. What people have done then, and I'll be showing that, but not immediately, is that they've used different detector techniques to pick out the different ones. So what I show here is that if I use as a detector something made out of gallium or chlorine or a different technique altogether, they go down to some energy. So if I take this one here, which I'll be showing in the next lecture, it doesn't even detect these neutrinos that come here. It detects the higher energy neutrinos. Or if I take gallium, then it can see the proton-proton neutrino. So people have used different experimental techniques that get you to the various parts of this. And for what I'm going to show today, doesn't matter which technique you use, which one of these spectra, the same phenomenon happens. And I'll try to show you that in a little bit. So the first experiment that was done that I'll talk about that saw neutrinos from the sun, which verifies that the reaction that's happening is the fusion reaction, was an experiment done in the Baksan laboratory in Soviet Armenia near Mount Elbrus. And it used gallium, germanium, a neutrino detector. This is under the mountain. It sits underneath a mountain so that it shields out any sort of effects that don't come from the neutrinos from the sun. And it measured the reaction. The neutrino comes in, reacts with gallium-71, and when it reacts with gallium-71, if it's an electron neutrino, it then makes an electron, and it makes germanium-71. And that's sensitive directly to the PP process, fusion process in the sun. They used 50 metric tons of gallium to do this, and from that, they extract just a few tens of atoms of, and this is doing it over many years. So this experiment ran for several decades, and they measured a number which is in units that I won't define for you, but it's solar neutrino units. 65. They measured and saw a flux. You can see that it's always significant compared to 0. This is 0, and this is time. So, and it's more or less consistent, and they measured it then to this accuracy. So they measure a flux. That flux came out 65.4 plus 3 plus 2. What are those numbers? This is the statistical accuracy. Comes from how well you measure it, and this is how well you know it from the errors in the calculations that you make, what we call systematic errors. So altogether, 65 has this pretty small error on it here, less than 10%. Yet, if I go and calculate everything I know from what I showed you in the first part of this lecture, the temperature of the sun, the size of the sun, the amount of material in the sun, the amount of material in the core, the reactions that happen in the core, the amount of nucleons there are, and so forth and so on, I can predict with pretty good accuracy, better than 10%, I can predict how many electron neutrinos come out of the core of the sun to give the temperature and everything that we see. And what was seen is that what was measured was 65 in some units, particles, electrons coming, neutrinos coming from the sun, while the prediction gave 140, 138. So we're only seeing a third or a quarter or half or something of what came from the sun. Maybe that was the trouble with the experiment. A different experiment was done in the home stake mine. This shows it. The prediction for how many would come, doing all the calculations of how the sun burns, everything I told you before, is here. What's measured is here. This is measuring it as a function of time in a very different experiment. This experiment uses a big vat, 100,000 gallons of cleaning fluid, which you use to kind of clean, expensive. And this reaction is looked for. An electron neutrino interacts with chlorine-37, makes argon-37, and what they would do is just let the vat sit there. Neutrinos would come in, and every week or so, they go into the vat and look and count how many argon-37s, which you see here, are detected inside the detector. And in this way, they determine how many neutrinos had been captured by this reaction here. So this could be predicted again if I know how many electron neutrinos there are. The number you expect from the sun is shown here. The number detected as a function of year is shown here. Again, if I look at this carefully, if I look at this and add it up over time, roughly a third of what we thought should be there were there. Lastly, maybe something's wrong with the whole picture. That wasn't really able to say anything about the sun itself. You couldn't point. You just had this thing sitting there counting interactions. So how do we know that it's really from the sun at all? Maybe the whole idea is wrong. The first experiment that was capable of seeing the neutrinos come from the sun itself is an experiment that I'll talk about later, but for this purpose, it's a huge vat of phototubes looking at pure water. It's called Kamiokande. That's a mine that it's in Japan. And in that experiment, they're able to actually see the products of the interactions and the direction they come from. And in doing that, they were able to then see that the reactions, the ones that they saw, came from the sun. The neutrinos come in and make an interaction like this. You can then see from the final electron ability to point back to where the neutrinos came from. They follow that direction pretty well because and this is a picture back of where the neutrinos that they saw came from. And you can see that they see the sun, basically. So the neutrinos that were detected were too few, roughly a factor of a third or a quarter or a half. But they are truly the neutrinos from the sun because we're able to point and see the events that are seen in a more recent experiment do come and image themselves into the position where the sun is. So that's the situation that basically put us in a very controversial situation in the 1990s and early 2000s. And that is that we now see that the neutrinos come from the sun. The burning cycle in the sun is undoubtedly what people thought it was, but for some reason we don't see the right number of neutrinos here on Earth. So in many meetings that I went to roughly 15 or 20 years ago, there were debates back and forth, mostly between nuclear physicists and particle physicists, whether particle physicists being concerned that maybe the calculations being done by nuclear physicists of the burning cycle in the sun and so forth was wrong, and that somehow the predicted fluxes were different, and so they were being challenged to basically prove that they could calculate the flux well enough. On the other hand, the other possibility is somehow the neutrinos, by the time they got to the Earth, were no longer electron neutrinos. That is, the neutrinos in coming to the Earth decided to change their identity to a muon or tau neutrino. That's what we call neutrino oscillations. And so those were the two possibilities, and we have to resolve those one way or the other. As I say, this was pretty hotly debated because both were extreme conclusions. One conclusion is that we don't understand nuclear physics very well, and we can't even predict how the sun burns. That's one conclusion, possible conclusion. The other is that we don't understand particle physics very well, and the neutrinos themselves have to have some feature that we don't know, and even have mass, which we thought was zero. So basically it was one or the other. It turns out it's the latter, and that's what we'll spend our time on here. So altogether, in the experiments that were done, that I show here, the predictions are up here, and the actual measurements were below that. So all the experiments either reflect an ignorance of how the sun burns, or the phenomenon which I'll describe later, which we know now is what happens, that there are what we call neutrino oscillations. After there were 6 different experiments around the world that were done, different techniques and so forth. 3 of them using this gallium that I showed you, 1 using chlorine, that was the cleaning fluid that I showed you. The last one that used water Cherenkov counters that was able to image. All of them gave a signal that was somewhere between 1/3 and 1/2 the number of neutrinos that were emitted. So this was the discrepancy that we had. Now, next week, I'll talk about all the kind of what happens in the phenomenon of these neutrinos changing identity, but for the purpose of today, we'll concentrate on just some conclusions from that. First, let's go back to the question of, now we say that neutrinos have some mass, oscillate from one to the other, which I need to address the next question, which I want to do before I talk about that phenomenology. So the fact that they have mass and the fact that they oscillate, which again I'll talk about, show you the evidence next time, is crucial for what I'm going to talk about next, which is the fact that we have said that there are only 3 neutrinos. Is that true? Or could there be other neutrinos? I mentioned, of course, that there could be other neutrinos if they were heavy enough. For example, if a neutrino happened to, since we know it has mass, if it happens to actually be more than half the mass of the Z particle, then it wouldn't affect the width of the Z particle, so there could be more. There could also be a class of neutrinos that interact differently. And this is a very popular idea that people use and develop in particle physics because it could solve many other problems that are unsolved in particle physics that would help maybe solve those. So it's a popular idea for people to suggest there might be what we call sterile neutrinos. By sterile, we mean they don't interact in the usual way, but interact in some other way. So it's hypothetically, you have a neutrino that's a neutral particle. It interacts only, however, by gravity. It doesn't interact via the fundamental interactions of the standard model. So that's the idea. Are there other neutrinos like that? So is there a 4th, possibly a 5th neutrino? Could it mix with the known neutrinos? And so forth. I would ignore this subject because it's only kind of a theoretical conjecture, except there is experimental evidence that maybe there is a sterile neutrino. And so I'm going to show you that, because you shouldn't walk out feeling that there's just maybe an idea that people have. There may be another neutrino. The evidence is not conclusive, but I'm going to show it to you so that you know that even though we say there's 3 quarks, 3 neutrinos, there is actually evidence that's presented, published, and not contradicted that there might be a 4th neutrino, and that's what I want to show you today. This is a complicated plot, which you'll understand better after next week, I hope, when I present it. But this is the mixing between the neutrinos. The mixing is put in an angle that how much do the 3 neutrinos mix with each other. And what's the mass difference between these neutrinos? They now have mass, but the muon neutrino, the tau neutrino, and the electron neutrino will all have different masses. So what's the mass difference? If I have 3 neutrinos, then this is the whole picture here, and it's what I'll talk about next week. The masses are quite small, and there's mass differences between the 3 neutrinos that can give 2 mass differences. And that's these here. These are the measurements that have been done. You'll notice this is a log scale here. The stuff up here is the results of the one experiment that now indicates there may be sterile neutrinos. And that experiment was done first in the 1990s at Los Alamos Laboratory. And then in a much more sophisticated experiment, it was done in the last 10 years or 15 years at Fermilab. And it shows evidence, if right, if correct, that there's another neutrino and there's mixing that's much larger. Mass difference is much larger. And this is puzzling, but I want to show you, since we're supposedly at the frontiers, that the question's not closed how many neutrinos there are. There may be more, and there's even evidence, and I'll show you that. So let's talk about this experiment. This experiment is pretty easy to understand conceptually, and I'll show you kind of how it works. This was done first at Los Alamos on the particle accelerator they have at Los Alamos called LANCE. It starts with protons and making pions, and the pions decay into a mu and a mu neutrino. And that muon, if you let it go through space, decays and makes new mu's and new mu bars, new e's, and positrons. So you make one neutrino here, and you make these neutrinos. And then you have a detector back here. That detector can be moved, or the interactions can be seen as a function of distance, and with that you can tell what the different neutrinos are. So the protons are produced at the accelerator. The pions make muon neutrinos, and the muons themselves, when they decay, make electron and anti-muon neutrinos. Notice there are no anti-electron neutrinos made. So this is the reactions that happen quite cleanly because it's done on an accelerator. There's no backgrounds particularly. And it makes 3 kinds of neutrinos, but not the 4th. So the question is, can you make the 4th by it decaying and changing its identity? In the detector, they then look for this 4th one. They look for the fact that you shouldn't have made any anti-electron neutrinos, and they look for this reaction. So to repeat, we look at the protons come in and hit a target, they make pi pluses, they make this kind of neutrino, nu mu. The muons that are here decay in time, they make these neutrinos. So 3 of the 4 neutrinos are made, but the electron antineutrino is not made, and so looking for this reaction looks for the fact that if they see them, presumably the neutrinos have changed identity one to the other, like neutrino oscillations. Okay. So they did that without going through the details of the experiment, which I show here. Just in concept, its size is something like tens of meters, 30 meters long. The energy of the neutrinos, in this case, is much higher than the solar neutrinos. It's something like 20 to 55 MeV. And there's a lot of detectors, about 1,000 phototubes. It's quite a sophisticated experiment, a lot of liquid scintillator. And they observed looking for antineutrinos. The conclusion is seen here. So if the experiment is right, they see anti-electron neutrinos, which you're not supposed to see. And they see 87.9 with an error of 22, plus or minus 6. This is systematic errors. This is statistical errors. But altogether, these errors are small compared to this size. And so there's good evidence, if the experiment's correct, that they see neutrinos of this neutrino oscillations, changing identity. But if you put in the masses of these oscillations, it's much larger mass than the masses we were talking about in the solar neutrinos. So they've made, presumably, this much larger neutrino mass difference, which is what I showed in the first picture. Neutrinos themselves are produced by the pions and the muons that I show here, and I just showed the kinematics. But let me skip that because of time. Then if I take the distributions, what's shown here is now fitting it. All this cross-hatched part here is presumably due, this part here is presumably due to neutrino oscillations. And so this is the data, and they put in this much for neutrino oscillations, and they get this mass difference. I showed it on the other plot, which is a much bigger mass difference than what we know from the solar neutrinos from the sun, that described the neutrino mass differences between the muon, the electron, and the tau neutrino. So now we've gotten a fourth one. It's not another mass difference, if correct, that would require us to have another neutrino of some sort that gave that mass difference, even though we thought there were only 3 neutrinos. That experiment then, what that mass difference is here, I show you, it's something like 1 eV squared, while the others were about a factor of 10 to 100 lower. So the neutrino mass differences that we saw before were something like 10 to the minus 3 or 10 to the minus 5 eV squared. This is a much larger mass difference, if true. So this is the experiment, quite controversial. That experiment then motivated doing a better experiment, which I'll show. This is just repeating the evidence. If the evidence is there, then when I talk about I'm not going to talk about this again next week, so let me just show it now. When I talk next week, I'm going to talk about these mass this is mass here. I'm going to talk about the mass differences down here in scale, and this one's up here. Mass difference is much larger, and this is the evidence that something like EV squared. So this large mass difference, if it's correct, I'll ignore completely next week. We don't know that it's correct, but I wanted to show you. But let's look at the signal. So if this is true, it would be explained by some sort of additional sterile neutrino. That is one that didn't appear in the quarks and neutrinos, and some theoretical ideas like the idea that you might have this, but it doesn't fit the rest of the picture that we have very, very well. So this motivated doing a better experiment. The better experiment, this was done in the early 90s. The better experiment was constructed to be started in 2002 at Fermilab and is, I believe, still taking data now, today. So it's still alive. That experiment was meant to either confirm or to reject what was done at Los Alamos. It was similar sensitivity to what the mass differences are that were seen in that experiment. So it was designed specifically to look for this effect at that mass difference and optimized for that. has different systematics from the different technique, different systematics from what was done at Los Alamos. Much better statistics, better data, a higher energy and more powerful accelerator. And they expected to be able to do it, or either to do or to disprove it at something like 90% confidence level. This is just pictures of it at Fermilab, which I'll skip. This is a picture of the experiment itself. That experiment is quite sophisticated. It uses something called a magnetic horn, which is a way to take the products of an accelerator and point all the secondary products which come off at all angles at your detector, so that the neutrinos that come out come into the detector primarily. There's some absorber to get rid of all the other particles, and then the detector detects the. I would say the sophistication of this setup, the sophistication of the experiment itself is comparable to the best experiments that have been done with neutrinos. So it can't be criticized that it wasn't carefully done. If there's a flaw, it's a human flaw. And it's something we always have to be careful of in science, and that is that most of us don't like to spend 10 or 20 years of our career trying to disprove somebody. It's a thankless job when somebody sees something that somebody has to go check it. It's necessary in science that we check that somebody sees something if it's different that we see or don't see. But most of us would prefer to spend our time trying to see something new than to disprove or check something that somebody's already seen. Unfortunately, in this case, there was no one different from the original group of people that saw and claimed the discovery at Los Alamos that was interested in spending 20 years of their life checking whether they were right. So the experiment, as sophisticated as it is, that has been done second, which I'll show you, was done by the same people. So there is the problem that we have in science, that it's not the human effect. Biases that we have as humans can affect the results. So it's not that I'm claiming that, but it's something that people should be aware of, and that we're aware of as scientists, that it's not 200% independent experiments because it was done by the same group of experimenters. Nevertheless, on paper and as a detector, it's a very careful experiment. So I don't have time to go through the details today because I ran behind a little bit. So let me jump to the conclusions. So they go through what's called mini boon at Fermilab. They see they have ways to actually image these different products in a very nice way. These are showing the differences in the patterns that they see in the detector, depending on which reaction they're looking at. And again, they observe this and they see the same effect of a neutrino and anti-neutrino excess as a function of the energy of the neutrinos. So, and it's consistent with the same data that they saw in the previous experiment. So the two experiments basically agree. The two experiments agree, and yet we're not sure that there's a sterile neutrino. So it's an unresolved question. About the only actual real problem, I think, is that it's the same group of experimenters. Otherwise, it would be an independent check of the same thing. This is the statement, if you want to read it, made by, this is quite recent, made by the leaders of this second experiment. So I'm just going to read it to you because it's an unsolved problem. Both LSND and mini-boon, that's the names of these two experiments, see indications of electron-neutrino, antineutrino appearance. But there are discrepancies in the energy distributions of the appearance signal that could or could not be related to oscillations. So there are some differences technically between the two experiments. You can criticize that they both see an effect, but it's not exactly identical. The analysis of all the high delta M squared data sets show that the models with several sterile neutrinos can give acceptable global fits. So if you take the experiments literally, you need to have not just one sterile neutrino, you need more than one. So that's not very comfortable. Reported incompatibility with sterile neutrino models, especially between the appearance and disappearance measurements, may be arising from the choice of test statistics rather than the underlying discrepancy with the data sets. So the way the data was analyzed in the two experiments used different statistical methods, and that may cause some of the difference between the two. Investigations of high delta M squared, that is the difference between the masses of the neutrinos, currently form one of the most active areas of neutrino physics, and many new experiments are being mounted or considered. This future program builds on the initial measurements of LSND and mini-boon discussed here and aims to provide a definitive exploration of new physics signals in the neutrino signal sector, such as sterile neutrinos. So you can see it's kind of an ambivalent statement by the leaders of these two experiments that are done. So whether there are sterile neutrinos in nature, there's many theoretical papers that want to push them. There's experimental evidence, but it's somewhat muddied by the fact that it's really by one group, and the two experiments aren't 100% consistent with each other, which might indicate that there's some experimental problems, not just new physics. And we don't know the answer. So being at the frontiers of physics, I point out that at this point, a popular idea that they're sterile neutrinos, and therefore more than just the three families and the three neutrinos that we know about, is a live question. There are experiments that are being put together to check this, so it's not that this will be unresolved forever. There's an experiment in Belgium. There's a new experiment at Fermilab. These experiments, I think, will resolve the question, and they're just about to be put together, about to start taking data in the next few years. So as you watch this subject, it's an interesting one. It's interesting because theoretically it's interesting. It's interesting because it's an unresolved question, which is always interesting to track. So the question of whether there are sterile neutrinos, whether there's more than the three neutrinos that go with the box that I keep showing you of all the constituents of matter, is an open question. There's some evidence there might be, but it's not definitive. And if there are, then we have, when I start talking about mass differences in the next lecture, we're going to talk, I'll only show this down here, that there's mass differences down here. The final issue that I'll show here is that you see the different colors on each of these. This has to do with the fact that once we mix the neutrinos, what I call an electron neutrino, or I call a muon neutrino, or I call having a certain mass, might be a mixture between them. And what's shown here is if I do the neutrino oscillation phenomenology, which I'll show you next time, that they end up being a mixture. The phenomenology to give different masses, unique masses, mixes the different neutrinos. So there's neutrinos that are called nu mu, nu e, and nu tau, which we talked about, but you might also talk about nu 1, nu 2, nu 3 that have unique masses, and then they're mixtures, and these colors are how they're mixed between the e, mu, and tau. And I'll show more about that in the next lecture. But in terms of the sterile neutrinos, I'm going to have shown you that, and from now on I'm going to not consider sterile neutrinos, but you know that I'm not ignoring it, it's a live subject. So everything I'll talk about next week is this on the left. It's the possible neutrino oscillations between three kinds of neutrinos, the ones that we talk about. And in fact, the evidence that I showed you just now is the possibility that there's a fourth one, much higher mass, that comes from this so-called sterile neutrino experiment. A couple comments just before I let you go. Even a small amount of neutrino mass has a big effect on cosmology and astrophysics. And what I show here is the effect on something that we'll talk about, and that's the structure, the small-scale structure in the universe, depending on the mass of the neutrino. So people often show plots like this, and we'll show it in the spring when I talk about cosmology a little bit. That gets affected a lot, and this is just showing it graphically, depending on whether there's a neutrino mass. So if you have a small, this is large-scale structure, this is small-scale structure. The lines through this are how much they'd be changed depending on the mass of neutrinos. So if you have neutrinos and the difference in mass is something like 2 eV, it's a huge effect. If it's a half an eV, it's less. This is data, so we know that the difference is something small. But the effects have a large lever arm, and so understanding these differences also is affected by, or what we know about them affects the large and small scale structure of the universe. That's because in the early universe, neutrinos were a real prominent player in the development of the history of the universe itself. This is just more of the cosmology effects of whether there's mass in the universe. I'll come back to this when we get past neutrinos and get toward cosmology. So I think that is where I'll end for today. And next time we'll do neutrino oscillations itself. As I said, it'll be a little bit more formulas and so forth, because there's no other way to do it than I've used so far. But I'll try to use those mostly as something you can look at in the notes, and I'll talk to them more than derive them. See you next week.